Welcome back, math friends. This is AP Calculus, section 2.3, day 2 notes. We are going to be continuing to talk about limits today and evaluating limits. One type of limit that we have not talked about yet is limits that involve absolute value. And what you need to know about absolute value limits is that they are always a two-sided limit, meaning that you have to evaluate the left-hand side and the right-hand side separately, because we know that in order for a limit to exist, left-hand limit and right-hand limit must agree. And so because of the shape of an absolute value graph, the V shape that they make, we have to make sure that what's happening on the left-hand side is the same as what's happening on the right-hand side in order for the limit to exist. So basically, it's almost like you're just doing two problems in one. The math isn't any more difficult than what we were doing in yesterday's lesson. So for example 1, if we want to evaluate the limit as x approaches 0 of the absolute value of x, we're just going to do this two sides. So we're going to start with our left-hand limit. So we will say this is equal to the limit as x approaches 0 from the left of the absolute value of x, which is equal to the limit as x approaches 0 from the left of, and the absolute value of x on the left-hand side is actually the line negative x. So this is going to be the limit of negative x. And so now when I plug in 0 from the left-hand side, I just end up with negative 0, which is 0. Now let's check the right-hand limit. This would be the limit as x approaches 0 from the right of the absolute value of x. Well, on the right-hand side of the absolute value of x, the equation is just positive x. And so when you plug in 0, once again, you just get an answer of 0 for the limit. So because these two came out the same, we can say that the answer is 0. The left-hand limit and the right-hand limit agree. And real quick, just to give you a visual representation of this, remember that if we were to graph the absolute value of x, there's no transformations here. This is just parent function. This is what the absolute value of x looks like. And if we are asking what is the limit as x approaches 0 of this function, on the left-hand side and on the right-hand side, both sides of our absolute value are converging on the same value, and that value is 0. So visually, our answer to this one makes sense. All right, letter B, new problem. This time, we have to find the limit as x approaches negative 6 of 2x plus 12 divided by the absolute value of x plus 6. So again, we're going to do left-hand limit and right-hand limit. Our left-hand limit is going to be the limit as x approaches negative 6 from the left of, and I am just going to up here factor this numerator. The 2x plus 12 can be factored into 2 times x plus 6, and I'm going to write it that way because of that x plus 6 in the denominator. So in my numerator, I'm going to have 2 times x plus 6. And then in my denominator, the absolute value of x plus 6 on the left-hand side is the negative side of the v, is the negative x plus 6, or the opposite of x plus 6. And so when I cancel out my x plus 6's, when I reduce, I'm left with the limit as x approaches negative 6 from the left of 2 over negative 1, which gives me a left-hand limit of negative 2. Now I'm going to evaluate my right-hand limit. So this is going to be the limit as x approaches negative 6 from the right-hand side. My numerator is still 2 times x plus 6, but this time the right-hand side of the v is the positive sloped side, is just the positive x plus 6. The left-hand side is always the negative, the right-hand side is always the positive, unless you have some sort of a reflection. All right, and so when I cancel out my x plus 6's, I'm left with the limit as x approaches negative 6 from the right of positive 2, which is just 2. So this time, my left-hand limit does not equal my right-hand limit. And because of that, this limit does not exist. Another topic that comes into play when we're talking about limits is piecewise functions. Here we are given a piecewise function that contains 4 pieces. G of x has 4 parts to it, and we are asked to evaluate those limits and then sketch a graph. I'm actually going to sketch the graph first, and then I'm going to evaluate the parts of the function. You can do it in either order. I just find it easier to sketch the graph first because then we can actually use the graph to help us answer our questions. So I'm going to go ahead and sketch a coordinate plane. And I know that my domain changes, like where my functions start and stop, have to do with this part of my function right here, right? When x is 1 and when x is 2. That's where I'm going to be switching functions on my graph. So I am going to just put highlighted vertical lines at x equals 1 and at x equals 2. And I do that just for myself. Okay, this is just so that as I'm graphing, it's going to kind of assist me. So I start from the left and I work my way across the function. The first part of the function is g of x is equal to x, which is a diagonal line through the origin with a slope of 1 for values of x that are less than 1. So it has a y-intercept of 0, and then it has a slope of 1. So it looks like this. Now it's only for values of x that are less than 1, so I know that it's going to intersect there with an open circle. And it just goes on forever to negative infinity on the left-hand side of x equals 1. When x equals 1, the value of g of x is 3. So that's just a closed dot right there at y equals 3 on my graph. Then between 1 and 2, so between my 2 yellow lines on my graph, the function is 2 minus x squared. That is a transformed version of y equals x squared. We know y equals x squared is just our standard parabola. So if the x squared is negative, we know that it is downward facing, and that positive 2 is a vertical shift up 2. So our parabola would start at positive 2, and then it would go right 1, down 1 for the next point. Okay, so I'm kind of making an invisible parabola right now. And what's really helpful is on your paper, if you're using a pencil, you can draw it and then you can just erase the parts that you don't need. Now, I'm going to try to do that, but things might get a little messy here with my Smart Notebook. But basically, I only care about the right-hand side of the parabola because I'm looking at the part of the parabola that lives between 1 and 2. So if I were to graph 2 minus x squared, it would have a y-intercept right here at 2. And then it would have a point that would go right 1, down 1. And it would have a point that would go right 2 from y equals 2. It would go right 2, and then it would go down 1, 2, 3, 4. So it would intersect right there. But again, the only part of that parabola that I'm interested in drawing is the part that lives between my 2 yellow lines. So this part right here is the part of my function. And it should have an open circle on the line x equals 1, because if we look at the domain right here, it's values of 1 that are less than x, not less than or equal to. We already have a closed circle at 3. But then less than or equal to 2 says that at 2, we should have a closed circle right there. All right, and then the final part of our function is for values of x that are greater than 2. So on the other side of my yellow line at x equals 2, and that function is x minus 3, which is a diagonal line that has a y-intercept of -3 and a slope of 1. So again, I don't want to graph the line on the left side of x equals 2, but I might put some dots in just to help myself. So the y-intercept would be right here at -3, and then it has a slope of 1, so it would go up 1, right 1, up 1, right 1. So right here is where it intersects the yellow line, but I know that that has to be an open circle because I already have a closed circle on x equals 2. And then I just keep going up 1, right 1, up 1, right 1. And so this line is the last part of my graph, and I'm going to draw that in blue just to match the rest here. Okay, so there's my function. Ignore the orange, ignore the green. The blue parts are the existing pieces of my piecewise function. And now that I have that graph, I think answering the questions about each of the following limits is going to be much easier. So for part A, it says the limit as x approaches 1 from the left of our function. Well, here's the line x equals 1, right? As we approach from the left, right here, it looks like the function is approaching a height of 1. So this limit is 1. Part 2, we're doing the limit as x approaches positive 1 of my function. As x approaches positive 1 with no plus or minus after it, that means that I have to do left-hand limit and right-hand limit. Well, I already know that the left-hand limit was 1. I just did that. But the right-hand limit is also going to 1. So since the left-hand limit is 1 and the right-hand limit is 1, I can say that the limit of the function as x approaches 1 is 1. Left-hand limit and right-hand limit agree. Part 3, I am finding g of 1. What is the value of the function when x is 1? That is my closed dot right here at x equals 1. G of 1 is 3. Part 4, I'm doing the limit as x approaches 2 from the left side of 2. So down here, I'm going towards 2 from the left. My function is approaching a value of -2 from the left-hand side. Part 5, I'm doing the limit as x approaches 2 from the right. From the right-hand side, I'm right here, and my function is approaching -1. And so then finally, part 6, what is the limit as x approaches 2? So I basically am combining parts 4 and 5 together, and since the left-hand limit was -2 and the right-hand limit was -1, I have to say that this limit does not exist because my left-hand limit and my right-hand limit do not agree. The final part of our notes today involves the squeeze theorem. And we talk about the squeeze theorem when we talk about limits because the squeeze theorem can help us evaluate limits that are difficult to evaluate for various reasons. But the idea behind the squeeze theorem is that if we have some function, g of x, that lives between two other functions that we know, f of x and h of x, and if we can figure out the limits of f of x and h of x, and we know that g of x lives between them, then we can basically force that limit to live between two known limits, and we can calculate it that way. So the squeeze theorem says that if f of x is a function less than or equal to g of x, where x is near a except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x approaches a of f of x has to be less than or equal to the limit as x approaches a of g of x. If f of x is less than g, then its limit has to be less than the limit of g of x. And if f of x is less than or equal to g of x, which is less than or equal to another function h of x, where x is near a except possibly at a, then the limit as x approaches a of f of x, which is equal to the limit as x approaches a of h of x, is equal to L, then because g of x lives between them, we would say that the limit of g of x has to equal L. I know that this is a little bit confusing right now, but I think if we walk through the following proof, it'll make a little bit more sense. So here's just an example that I have done for you to show you the steps in the process. It says, show that the limit as x approaches 0 of x to the 4th power times the sine of 1 over x is equal to 0. So they've actually said the limit is 0. You just have to show that it's 0. So first, we cannot say that this is equivalent to the limit as x approaches 0 of x to the 4th times the limit as x approaches 0 of sine of 1 over x, because the limit as x approaches 0 of sine of 1 over x does not exist. And if you try to graph it on your calculator, you'll see that there's a vertical asymptote at 0. And so we did a problem like this the other day where it was oscillating, but it never settled on a value between -1 and +1. And so we couldn't determine the limit, and we had to say the limit does not exist. So that's the problem, the initial problem with this type of example, is that because of that sine of 1 over x not existing, we can't just use the limit laws and say, well, this is a product of limits and evaluate them and multiply them together. That doesn't work because one of our limits does not exist. But what we do know about sine functions, especially with an amplitude of 1, is that the value of the function will live between -1 and 1 on our y-axis. So we can set up the following inequality right here. We can say that -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. And if you were to graph sine of 1 over x, you could show on a graph that the entire graph along the y-axis lives between -1 and +1. And then next, we're going to introduce that x to the 4th power, because we've created a sandwich inequality here, or an equality with 3 pieces, a left side, a middle, and a right side, right? We've squeezed our function in the middle that we're trying to find the limit of. So now we would say, well, if we multiply the left side by x to the 4th, the middle by x to the 4th, and the right by x to the 4th, as long as we do it to everything, we're following the rules of math. So on the left side, -1 times x to the 4th is going to be our -x to the 4th is less than or equal to, and then we have our x to the 4th times the sine of 1 over x, which is less than or equal to +1 times x to the 4th is x to the 4th. So now we have that function that we want in the middle. And now we can take our limits, right? So the step that's not shown here is showing that the limit as x approaches 0 of -x to the 4th is less than or equal to the limit as x approaches 0 of x to the 4th times sine of 1 over x is less than or equal to the limit as x approaches 0 of +x to the 4th. Well, right here, we know that the limit as x approaches 0 of -x to the 4th is 0. That's direct substitution. You plug 0 in, 0 to the 4th power is 0, right? So this is 0, is less than or equal to, in the middle, we still have this limit we're trying to figure out. The limit as x approaches 0 of x to the 4th times the sine of 1 over x is less than or equal to, but again, the limit as x approaches 0 of x to the 4th, that's 0. So notice that we've sandwiched, or we've squeezed, the limit that we're trying to figure out the answer to between 0 on the left and 0 on the right. So if 0 is less than or equal to this limit, which is less than or equal to 0, then that means that the limit as x approaches 0 of our function has to equal 0. So let's try this last example together. Note it looks extremely similar to the one that we did before. The only difference is we don't have sine of 1 over x, we have sine of 3 over x. But we are going to follow the exact same process. Now, I really want to stress to you that when you are using the squeeze theorem, notation is very important. You can't skip steps. If this were an AP test and you were using the squeeze theorem, they would be looking very carefully at your notation and making sure that you didn't make any assumptions or drop any of your limit notation along the way. So be very careful, okay? So the first thing that we're going to do is we're going to say that we know, just based on the behavior of any sine function with an amplitude of 1, that sine of 3 over x has to live between -1 and +1, right? All the values of that function will be between less than or equal to, or 1 would be less than or equal to it, and it would be less than or equal to 1. The next step is to reintroduce that x to the 4th that's being multiplied by the sine of 3 over x. So we're going to multiply x to the 4th times -1. We're going to multiply x to the 4th times the sine of 3 over x, and we're going to multiply x to the 4th times +1. On the left side, we're going to get -x to the 4th. In the middle, we're going to get x to the 4th times the sine of 3 over x, and on the right, we're going to get +x to the 4th. Now we bring in our limit, and we say, well, we really want to take the limit of each part of this inequality. So we're going to do the limit. I'm going to switch colors here. We're going to do the limit as x approaches 0, the limit as x approaches 0, and the limit as x approaches 0 of what was there before. So of -x to the 4th, of x to the 4th times the sine of 3 over x, and of +x to the 4th. This we can do by direct substitution. This we can do by direct substitution. When we plug 0 in, the limit as x approaches 0 of -x to the 4th is 0. And over here, the limit as x approaches 0 of x to the 4th is 0. All right, we have just squeezed our limit between 0 on the left and 0 on the right. So then the way that we write our conclusion, you may have seen this before in mathematics. This little triangle made out of dots just means therefore. So we can say therefore, by the squeeze theorem, the limit as x approaches 0 of x to the 4th times the sine of 3 over x equals 0. So this is our conclusion for our problem. These proofs aren't hard. You just have to practice them a few times to get used to the process and to get used to the notation of them.